Okay, so we are live. We're going to start at 7 p.m. Okay, so we're gonna wait like 1 or 2 more minutes and then we're going to start with the event. Okay, so it's 7:02, so I believe we can start. Thank you everyone who is here, and thank you to everyone who is taking time out of their semester to sort of attend our events and learn from them and hopefully benefit. So this is part two in our machine learning series. We are doing a machine learning series for the month of October. It is a three-part series. We finished part one last week. However, do not let that intimidate you if you did not attend it. Part one was simply an introduction to Python, so it was a standard, typical, coding workshop. where you're just coding, no ML really related. We're going to start with sort of the stepping stone to ML today when we take over on the machine learning libraries for using Python, such as Numpy, Matplotlib, Scipy, and Pandas. So for those of you who don't know me yet, although if you've seen any of our other events, you probably do by now, my name is Hala and I am the SC lead for this year. So two members of my core team will be presenting today. So Eli and Iyad will be presenting today and they will cover these Python machine learning libraries. So before we can get started and actually begin with the workshop, let me just tell you one important thing. This workshop is going to be very hands-on, so there will be a lot of code involved. So consequently, because of this, there will be some, follow-up content. I will be sharing the slides, the notebooks, and everything else. So please, if you haven't RSVP'd on our platform, please do so before the end of the event. So you have from now until the end of the event to do so, just so that we can actually have access to your email and email you this content. Otherwise, there's no way for us to know who really attended and who did not. Okay, so moving on, one important thing we always have to highlight is that we have a zero tolerance policy for harassment or discrimination of any kind. Please do not bother each other. Do not join events if you're just going to be rude. Do not comment foul things um, or just discriminate against other people based on their gender, religion, politics, or race, or anything else. So please, this is a positive community. We have a zero tolerance policy for this. This is actually Google's community code of conduct. So please keep that in mind. And the final thing I want to highlight before I pass this on to the core team for them to present, Iyad will be starting, I believe. Before I do that, let me just highlight one last thing, and that is Quick Labs. So if you've signed up as a member on our platform, you probably know what Quick Labs is by now, and if you've seen any of the other events, Quick Labs is basically this platform, just like Coursera or Udemy or somewhere else, where you can just take these courses online. These are specifically related to Google Cloud, and the Google developer communities are kind enough to sponsor us with Quick Labs by offering us one free month access every month. And every month there is a monthly track where the track is basically a list of courses that you should take inside this month that will have that if you complete, you will get rewards at the end of the month. So rewards can be anything between t-shirts, a gift box, or even maybe some limited edition Google electronics. So please keep that in mind. And the reason we are doing these machine learning events in this month specifically is because October is our machine learning month. So please, if you are a member already on our platform, you will have received a PDF from us, especially yesterday. We sent another reminder with the PDF how to get your free month on Quick Labs, how to sort of what the quests are for this month, so what you should solve. So these are the 5 quests you should solve for this month, and other details. For more info, you can join our Slack and ask questions. So without further ado, let's get started. I'm going to pass this over to Iyad, who's going to start with the presentation with the first Python library. Okay, Iyad, you can start
Okay.
sharing and we can start.
Yep. Okay. So hello everyone. We'll be starting by talking about NumPy. Actually, before we do that, one quick note: in the description of the live stream, you will find links to all notebooks which contain the explanation and code we'll be working on today. If you want to, you can go open that link and follow us and follow up with us. This way, you can edit the code live and experiment yourself. You can also keep these notebooks after we finish with our events to as a reference and to continue doing experimentation. Okay, so let's get started. Basically, NumPy is one of the most important libraries you will use as a Python program. It's used in almost every field of engineering and provides the tools to perform complex mathematical computations in Python. Okay, at the core of the NumPy, there's the class called the ND array. Basically, it's just a table of usually numbers, which has the following parameters. It has a dimension, which is the number of axes. Say a 2D table as shown here. A 1D table would be a list. Let's say a 3D table would be a stack of tables, etc. The shape, which defines the numbers of rows and columns, or for CD list, let's say it will have rows, columns, and number of elements stacked together. And the size, which is the total number of elements in the array, and the data type of the data stored in the array. That could be an object, a string, integers, floats, doubles, etc. Okay, so how do you create NumPy arrays? At first, we definitely need to import the NumPy library. To do this, we just have to write import NumPy as np after having installed it. Once that's done, we can start creating our NumPy arrays. The simplest way to create a NumPy array is by using Python lists. You just create a list and wrap it with np.array. This will result in a NumPy array from this list. In this case, this is the output we'll have. We'll have a 3 by 2 array. It has 2 dimensions. The shape is 2 by 3, 6 elements, and data type in it is float 64. Another possibility is to actually create an array of zeros using numpy.zeros. This will result with an array with the given shape containing all zeros. We can also definitely create arrays with random numbers, random integers in a given range. And one of the most important ways of creating an array is the line space. Basically, it will allow you to create an array that starts at a number, ends with a number, and has n number of elements. This is very useful when discretizing data. Say you want to create a discrete time array for doing kinematics computations or something. You can do that. A very similar function is also numpy.arrange, which will allow you to it's very similar to the Python range function. It will allow you to specify a start, an end, and the step size. It will then fill up an array with as many numbers as possible with this given step to go from start to end. One last way of creating an array is actually by repeating an element of your choosing. So in this case here, we're repeating a string element, which is DCS, 5 times, and it will result in the following array. Yep. Something went wrong here. Anyways. Okay. Another thing you can do with NumPy arrays is revert back to a Python list. To do that, you can very simply add the toList method called the toList method of any Python NumPy array. This will result in the list with the same exact data. Okay. You are also able to actually save and load NumPy arrays to disk. This is really, really useful when pre-processing your data before loading it into a training script to do machine learning. You can simply np.save any array and specify your file name and np.load to load that array back. Okay. Any questions?
Nothing yet.
Okay, so let's continue.
Great. Yeah, sorry to cut you off. Like you just mentioned something real quick, and I want to actually highlight it. So the importance of these libraries, like why are we even doing this event to begin with, is because of how important they are in machine learning. So like if you can tell us exactly like how crucial they are, or how you cannot really move on to machine learning with Python without these libraries.
Okay. Speaking about NumPy specifically, to start with, basically it's the library that allows you to do all the heavy number crunching in Python. Most ML libraries actually use NumPy as a backend to solve all the mathematical systems that allow ML to work. Say, for example, TensorFlow actually takes all its input in the form of NumPy arrays that have to be pre-processed and well formatted to be able to use for ML. Even if you want, you can even write your own ML scripts from scratch without using any libraries, using NumPy, which is a really great tool and greatly optimizes the performance of running your computations. It's much, much faster than actually using for loops or any equivalent. Okay, so let's get started with array manipulation on NumPy arrays.
Before you do, we actually just got a question.
Okay. Sure.
What's the difference then between arrays and lists?
Basically, a NumPy array allows you to do mathematical functions directly onto the array as a whole. It can behave either as a vector, as a matrix, as a list of scalars, etc. Python lists are just a data structure that contain objects. You can't really work on those objects as a whole. You need to access them individually and apply your operations. This is why Numpy is much more optimized because it removes the need for doing for loops. Okay, so array manipulation. Okay. One of the most basic operations you can do on array is slicing or indexing. Basically, this allows you to access elements in an array. Suppose we created an array which is the square of the numbers from 0 to 10, to 9 in this case. By simply printing A with the index operator and 2, we'll be accessing the element at index 2 in that list. We can also access elements in a range. In this case, by specifying 2 to semicolon 5, we'll be accessing all the elements between indices 2 and 5. In this case, the first index is inclusive, while the last one is exclusive. So in this array, if we go back, we'll be accessing elements 4 at index 2, so 4, 9, and 16. In this case, index 5 is 25, which is excluded. Fancy thing you can also do with NumPy arrays is actually get elements given an array of indices. In this case, specifying we want to get the elements at indices 0, 3, and 5, we can get the following outputs. Okay. Another thing is you can actually apply conditions inside those indices. Say I want to get all the numbers inside the array that are larger than 5. You just write inside the index operator, a bigger than 5. And this will return you all elements of this array larger than 5. Another useful thing to do is slicing. Just as with Python lists, you can actually slice NumPy arrays. In this case here, we're telling it to take all elements from start to position 6, and then take set every second element to 1000. Basically here, the semicolon operator before the 6 means take everything up to 6. And the other semicolon 2 is a step size. So it will take every second element and set it to 1000. In this case, we actually modified the data inside the array by accessing specific elements using their indices. We are also able to use a similar idea to reverse an array. In this case, we're telling it to take all elements of the array and with a step size of -1. So it will basically go from end to start. And you result with an inverted array. Note actually that the previous operation modifies the values inside the array object and does not create a new instance of the NumPy array. Okay, the same slicing and indexing concept can be applied to multidimensional arrays. In this case here, we're creating a 5x4 matrix. And in the case of higher dimensional arrays, we can just add this individual axes by using comma-separated tuples. In this case, say we want to get the element at row 2 and column 3. So row 2 and column 3 will be getting a 7 by doing it this way. It's also possible to get an entire row as a 1D NumPy array by just specifying a single index. In this case, how actually NumPy arrays work is we have multiple nested arrays to form a matrix or a 3D matrix, etc. It's also possible to access a column directly by specifying here a 2-point operator, which will tell us to take all the elements on the first axis, aka the rows, and a second element to specify what column not to take. In this case, column 1, so this column. As you can see, this is the output. Okay. NumPy actually provides us with methods to add and remove elements from array. But one thing, in NumPy, it's impossible to actually modify the attributes of arrays after being instantiated. So an array has a fixed shape, a fixed size, a fixed data type. So these methods have to return us a new array, as you will see below. Okay, so here we're creating a new array to do our experimentation on. Our first method is append, which will basically insert an element at the end of the array. In this case, we're inserting 5. It's also possible to insert a list of elements at the end of that array, as you can see here. Similar to append, we have insert, which will allow us to actually insert an element or an array into a specific location in our parent array. Say, in this case, we're inserting a 5 at index 2. or here this list as index 3, which will result in the current output given our array defined above. It's also able to delete elements from array given their indices. So we can just np.delete from A, index the element at index 4, which will result in a new array without this element. It's also even possible to pass this as an index, a list of multiple indices, which will actually delete all these elements from our array. Another very useful operator used when pre-processing data is np.unique. This will ensure that you don't have any duplicates in your data set. It will simply return a single instance of every element in that array. Okay, any questions before we continue?
Nope, nothing yet.
Okay. So let's talk about transposes. As you know, we can transpose a matrix. Basically, we're flipping the rows and columns. Numpy actually lets us do that really simply. We just call the actual array .transpose. It will result in a new array where the rows and columns are flipped. As you can see here, our first row is 0, 1, 2. In the other output, it's actually now our first column, 0, 1, and 2. Transpose is actually a very complex method that can be used to do multiple custom transposes. When applied on a 3D array or a non-dimensional array, it will basically flip the axis. So basically, it will just reverse the entire order of axis from end to start. So if we have an array that has shape 4, 3, 2, it will have its new shape after applying the transpose will be 2, 3, 4, basically reversed. In this case, this is a higher dimensional reversal of rows and columns. Okay, you can also define a new custom order for your axis in the transpose method. In this case, we're starting with a 4-dimensional array with shape 2, 4, 3, and 5. By using this method here, we're telling it to set the second axis of aka index 1 as the first axis of the new array, the third axis aka index 2 as the second axis of our new array, the first axis of the original array as the third axis, and the last axis will remain the last axis. As you can see here, the shape of the array has changed to reflect our change here. So the second axis is now the first, third axis is now the second, and first axis is now the third. And the last axis has kept its place. Basically, in this case, the data inside the array is not changing. It's only how it's actually formatted as an array that's changing. Another thing we can do with NumPy arrays is actually joining and splitting arrays. We have two ways of doing that. We can either join and split arrays vertically or horizontally. To stack arrays vertically, we'll use a method called np.vstack. Given a tuple of arrays, here it's 2, it can be more, it will just stack them vertically. So as you can see here, this is array B and array A and array B. It will result in this longer array that is basically the two arrays stacked one over the other. Similarly, we can do the same thing horizontally using the hstack method. NumPy also provides the methods to do the invert of this thing, which is to split the array. In this case here, we're telling it to split the above array into 3 new arrays vertically. As you can see, this is our output. It will return a list of NumPy arrays. The same method, hsplit, can also be used for horizontally splitting arrays. Works identically as vsplit. Okay. Our last thing about array manipulation is sorting. NumPy provides us the methods to actually sort arrays. Given an array of random numbers in a random order, we are able to very quickly sort through them to have them in a neatly ordered list. That can be either incremental or decremental. You can pass that as a parameter to the sort function. Another really useful function is Arcsort, which will basically return us the indices of a sorted array. In this case, if we have multiple arrays, say representing multiple columns of a table, we're able to solve all these arrays as a function of one column. So in this case here, we're actually sorting array A with Arcsort. Those are the new indices for array A. Those indices are then applied to arrays A and B to obtain two new arrays sorted depending on the values of array A. This is really, really useful in machine learning when you're looking to do interpolation or anything like that requires to have actually clean, continuous data. One last thing about arrays, we can also search through arrays really quickly. So here we have a random array. We're able to get the actual index of the maximum of that array and the index of the minimum element in that array. This in machine learning is practically used at the output of neural network models to identify the element that the classification model has decided to use, basically the element with the highest probability of being correct. Okay, so questions?
No question.
No questions. Okay, so one of the best uses of NumPy is for mathematical operations, as we said before. This way, NumPy is actually able to apply all mathematical functions on all elements in an array in one step. So instead of having to loop through every single element in your list and say add them together or do whatever operation, you can just apply the operation directly on the entire array. So in this case, we're actually creating two arrays to work with. And we can start applying basic arithmetic operations. So a plus 2, array plus scalar, will actually add the scalar to every single element in that array, as you can see here. NumPy also provides equivalent methods to the standard Python operators, which is np.add, and works basically the same. We're also able to subtract elements. Here we're actually subtracting an array from another array, which will do element-wise subtraction. Basically, first element will be subtracted from the first element of the other array, etc. Same for multiplication. In the case of one-dimensional arrays, this will do element-wise multiplication of those elements. And same for division. Here we're dividing actually an array by a scalar, which will result in the following output. Where NumPy actually shines and where you will see the biggest performance gain is when applying more complex mathematical functions. Say we have this array A with the following values in it. We can actually take the cosine of this array, which will apply a cosine to every single element in the array. We can take inverse cosines. Same for literally every mathematical function you can think of. We have the hyperbolic sines, cosine, tangent, etc. We can take an exponential, the logarithm of that value, all on the element-wise on all the arrays at once. What NumPy will do actually is it will turn this array data structure into a C list. It will do all this heavy processing in compiled C code, which is much faster than Python, and then output the result back to Python. This is why you see this huge performance gain when using NumPy. Okay. Question before we start with the next thing?
Yeah, we just got one.
Yep.
Is NumPy also good for storing and manipulating objects? Because the examples shown are just numerical.
Yep, definitely. NumPy can store any Python object, be it a string, any custom class to code it. But in general, it's most commonly used to store and process numbers, as it has all these methods that can work on those numbers element-wise much faster than using loops. But yep, definitely you can store objects in Python in NumPy arrays. So let's take an example here where we actually make use of NumPy's Fourier transform system. What we'll do here is we'll create two signals, one at 4 Hertz and the second at 7 Hertz, and apply a Fourier transform to the output. Here we're defining some starting parameters, our sampling frequency, which is basically the number of samples we'll be creating, the step, and a sampling interval. First thing to do is to create a linear time axis. For this, we can use the np.arrange method. This will create an axis that starts at begin time, here 0 seconds, and ends at 5 seconds, with a predefined sampling interval. This will result in a linear array where each element while elements are equally spaced. This is perfect to use as a time axis when modeling physical systems. So we can start by creating our first signal, signal 1, which will be a sine function with a given frequency, and will take our time. This will actually result in a new array with this function applied over all the elements of time. So basically, for every element of time, we will be applying a sine function to it. Same for signal 2, where we're creating another signal at 7 Hz. We can then actually sum those signals together, signal 1 and signal 2, to create a complex signal with both those frequencies. Now we can actually plot the signal. We're using Matplotlib for the plotting here. We'll get to this later. But basically, this is our output. We can see we have oscillations at 7 and 4 Hz. Now let's actually apply our Fourier transform. Numpy provides us with many methods to apply Fourier transform. One of them is FTT, which basically, given a signal, will result in a new array, which is the Fourier transform of this array of signals. Okay, we'll do it after doing some normalization here, and we'll also excluding the sample frequency from the plot to not have a peak at that. We actually get the Fourier transform of our signal, which here contains two peaks, one at 4 Hz and one at 7 Hz. This is really useful when processing sensor data with Numpy. Okay, any questions about that?
We have one about the methods before. What happens if we have a mathematical exception with our cosine and sine?
Okay, anytime you have a mathematical exception, the Numpy will actually result a value error. It will throw a value error exception you can just handle. It's also possible to have Numpy output this exception as a NaN value. When processing large arrays, it will just replace the actual value with not a number. So maybe let's try that. So let's come here and create a new code block. Okay. A new code block. Let's create an array A, which is np.array of, let's say it has an array of 2, 3, and 4. And we're trying to take the arc cosine of this array. Let's give it a value that actually worked for the start. So if we actually print out np.arc cosine, oh my bad, I actually ran that. Arc cosine of A. Just wait for it to process. Okay, let's run it now. Oh, Numpy is not defined. Let me rerun the whole thing. I'm sorry for the delay. It's basically this when using Colab, the actual code processing happens on Google servers. So it might take some time to actually load back those results, especially when rerunning the entire notebook. Okay, that's weird. Let me just refresh that. Technical problems, sorry for that. Okay, so I think we're good. Let's come. Okay, that's our example again, and let's rerun that. Let's just give it a second. Okay, still freezing for some reason.
In the meantime, we have a question.
Yep.
Is there any way you can use NumPy on a local system, or should it always be on the cloud?
No, NumPy can definitely run on any installation of Python. Just pip install NumPy, and that should install it on your system. So right here, we're using the cloud simply for ease of sharing, to be able to share this code with you, and to not have to spend time on setting up NumPy and all of Python on all of your computers. What we can do, if you want to, if there's demand, we can actually make a small guide that we can send you after this presentation about how to install all these libraries on your local machine. Okay, so, let's see. Okay, why is this thing so slow? Okay, wait, I'm gonna stop screen sharing for a second just to be able to actually rerun this thing. Seems like the screen sharing is actually slowing it down. So be right back. Let's rerun this. Okay, so sorry for the delay, guys. And technical problems can never be expected. Okay, so I think let's continue from here. Okay, so let's continue. Another great use of NumPy is actually in statistics. NumPy will provide us the methods to perform a vast variety of statistical functions on given NumPy arrays. So some examples, we can get the minimum of a list, the minimum element of a list of data, the maximum. We can get quantiles, basically out what's the Q1, Q2, Q4, Q3. Same for percentiles of any given number. Let's see here. The output haven't loaded up. Let me just do a quick thing here. Import NumPy as MP, and let's run things from here. Okay, so given this array of random numbers, we can get the minimum, the maximum, which is 99, the first quantile, 25 quartile, 25%. Save for the 71st percentile. And another very useful function is actually CumSum, where you can get a cumulative sum of the elements of the array. So running it on that, we will get the following outputs. Numpy also provides us method to compute averages and variance in the arrays. Here we're creating a random array of integers. So we can get the median, the mean. Basically, it's the arithmetic mean in this case. We can get a weighted average given another array of weights. We can get the weighted average of this data. And definitely, we can also get our variance and standard deviations. Those are really useful actually in machine learning, because at the end of the day, machine learning is just really advanced statistics. So it will be very useful to be able to perform statistical analysis on your data while pre-processing it to know how to best design your models. Another thing that Numpy shines at is actually doing comparison and logical operations on arrays. Say here, we are able to directly compare arrays to each other. In this case, it will actually compare those arrays element-wise. You're required to actually have two arrays of the same size. Here we're creating two arrays, one of given data and other one of random numbers. And if we perform comparison on those arrays, it will result in two other Boolean arrays, where each element of the array is the result of the comparison of the two elements of arrays A and B. We can also use a method called np.where, which will return us the indices where this Boolean array is true. This can be shorthanded as having directly np.where a smaller or equal to b, which will result in the indices of elements where element in A is smaller than elements in B. It's also possible to directly apply logical operations on NumPy arrays. Say you have two arrays of Boolean values, you're able to apply a not, an and, an or, XOR, NORs, NANDs, anything element-wise on those arrays. This is very useful when working with Boolean data, with large amounts of Boolean data. You need to quickly run through a specific Boolean function. So let's talk about the truthfulness of an array. As you know, an array has multiple elements, which could be true or false. So there's no way of actually determining if an array in its entirety is true or false. For that, NumPy gives us actually two methods. We have two choices here. We can either say that check whether all elements in this array are true, np.all a, which will return whether all elements in the array are true, or whether any individual element is true, np.any. In this case, if we run this code, we get the following output. Here we have some false elements in the array, so the entire array is false with np.all, but we also have a few true elements, so np.any will return a true. NumPy is also really useful for performing. Actually, before we do that, any questions?
No questions.
No questions. Okay. So NumPy is also really useful for doing matrix operations. As we all know, basically matrix addition and subtraction is really straightforward. It's just element-wise, so we can just use the pre-existing operators we learned earlier: plus, minus, subtract, etc. For array multiplication, NumPy actually provides us with a custom method called np.matmul. This method will return the matrix multiplication of two matrices. In the case where the dimensions of those matrices don't allow for their multiplication, NumPy will actually raise a value error that you can handle in your code. The same matmul operation actually works on stacks of matrices. So in this case here, let's create two stacks of matrices with the same dimension, with dimensions 4, 3, 3. Basically, it's a stack of 4 3 by 3 matrices, and we can multiply them together. This will result in the multiplication of every matrix in the stack by its equivalent matrix in the other stack. As you can see, multiplying two stacks of 3 matrices will result in one stack of 3 matrices. Oh. Another thing, questions? Okay, let's continue. Another thing NumPy is really useful at is vector operations. You can actually, in NumPy, you can simply define a vector as a one-dimensional array. It can be of 2 elements, 3 elements, or even n elements if you're working in n dimensions. So here we're defining a 3-element 3D vector. 2 3D vectors, 3 3D vectors actually. Okay, you are also able to define stacks of vectors. Basically, it's a 2D matrix where each row in the matrix represents a vector. Here we're creating one predefined vector stack and a random vector stack. You are able to perform addition and subtraction on those vectors, same as we learned before, element-wise. So here we're adding up 2 vectors together. Basically, first row of the vector stack B with vector A. And you can also apply those subtraction addition on an entire vector stack row-wise. So each vectors of the same index will be added or subtracted together. NumPy also allows us to perform the cross product of vectors, which will result in another vector that's perpendicular to both. It can be also applied on individual vectors or stacks of vectors, as we see here. Okay. For the dot product, things get a little bit more complicated. For 2 simple vectors, it's really easy. You can just use np.dot to get the scalar dot product of those vectors. But in the case where you have a stack of vectors, np.dot will actually return the result of the matrix multiplication of those two matrices, because at the end, a vector stack is just a matrix. So to circumvent that, we can use a function called itSum, where we can define a series of operations, which are basically chaining addition, multiplication, and transpose operations, and apply that to our 2 vector stacks. This expression here will actually result in the row-wise dot product of those vectors in the vector stack. In this case, in the case of a 3-run vector stack, we get 3 scalar values. np.itSum is actually a much more complicated function and can be used for a wide range of functions. You can check its documentation at the link below for more info. Okay, to compute the norm of a vector, what you usually do is to actually take the square root of the power of each of its components. In NumPy, this can be done as follows. But as you can see, this is complicated and it changes multiple elements. So another way of doing that is to actually take the dot product of the vector with itself and then taking the square root of that. This will result in the exact same output. Okay, so that's it for NumPy. You can find a few resources online at those links. We have the NumPy Learn website, where it says a lot of guides on how to use NumPy, as well as the official NumPy documentation. Another good note is QPy, which is a re-implementation of NumPy's methods using GPU computing. This vastly improves performance when doing especially when doing machine learning and working with huge data sets. Okay, so before we go back to Pandas, any questions about NumPy?
No, there are no questions.
Okay. In this case, let's start up with Pandas. Pandas is an open source data analysis tool written in Python, which is which is often used for pre-processing data in machine learning. It allows you to read data from a wide variety of formats, XML, CSV, JSON, databases, and convert it into Python data structures to be used in machine learning. In Pandas, we have two main data structures are the series and data frame. To create a Panda series, the simplest way is to actually use a Numpy array. As you can see here, we create a Numpy array, and then we can create a series from this Numpy array. Printing out the result, we will get a series of data. In this case, it contains strings, so objects. Data type is object. You can think of actually Pandas series as tables of values, where each element has its own index or ID. Pandas series can also be created from Python lists. No need to use ND arrays all the time. To access elements in a Panda series, you can do so just as you would access any element inside the NumPy array or a regular Python list. You can use indices and the slicing, just as we saw before. All the same rules apply here. But on the other hand, Pandas also allows us to do a few more advanced things. By using the lock and ilock functions, this allows us to actually index arrays with labels. So creating this array here where its indexed by where its indices are actually labels, we're able to use the ilock method attribute to access elements by their index, or the lock attribute to access elements by their label. In this case, we're doing the same functionality in three ways: by directly accessing the data in the series, by using the ilock method to force it to access data using indices, or by using the lock operator to access this data using its labels. Here, what we're doing is we're getting every element between D and E. Oh, actually, here we're missing an element, so it's D and F. Okay. It's also possible to perform binary operation on series, basically addition, subtraction, all these things. You can just get two Pandas series and add them together, subtract them together, etc. In some cases, you might actually have series that have a different number of elements. In this case, we use what's called a fill value that will be added to the series with missing elements to match the size of the other series. Here we're using a 0, so this will result in the addition of these two series. And when element 1, series 1 doesn't have an element, a fifth element, it will just replace it with a 0. So we'll have 0 plus 8, which will give us an output of 8. Some other useful methods of the Panda series are count, which return the numbers of non-null observations in the series, basically elements. We have the size method, which returns the number of elements in the array, is unique, which will return if we have all the elements of the series are unique, etc. There's a lot of methods that can be applied on Panda series. The Panda data frame is what's actually most commonly used. A Panda data frame is basically a table with rows and columns where each row and column has its own label. In this case here, we're creating a list data frame, machine learning with Python, NumPy, Pandas, and Matplotlib. Each one is its own row in the table. It's also possible to create tables with specifically named columns using Python dictionaries. Here we have a dictionary that has a label and an array as the actual elements. So this will create us a list of people and their major. All these things can be done using the Pandas data frame method, where you just pass it out your input data, either a list, a dictionary, an ND array, etc. Okay. You can also, how do you access columns in Pandas? In Panda data frames. Here we actually created this data frame given the following dictionary. We are able to actually access specific columns of this data frame by simply passing them as an index. Here we're passing them an array of columns, of column labels. So given this array, we can say this data frame, we can access the name and address of those people only, truncating everything else. This can be very useful when getting a large input data sets and having to filter them for the required data. It's also possible to use the lock and ilock methods as described before to access specific rows of this data frame. Here you will actually access every single attribute in that row. Say, in this case, we're accessing name, age, address, qualification, etc. Here, the second name is the actual label of the data that you can see here. When working with loads of data, you'll definitely have to visualize part of it. But printing out the whole data set can get really cumbersome. So for that, Pandas provides us with two methods, head and tail, that will allow us to print the first n or the last n elements of our data frame. This is really useful when verifying that the operations you're doing are correct without having to print your entire data set, which can be in the thousands of lines. So right here, we're creating a data set with 450 elements, which are basically grades on first, second, and final exam. And we're able to access the first 10 elements using data frame.head and passing it a number of elements. Same as for accessing the last 5 elements here. Okay, I think, yep, that's it. Pandas can also be used to handle missing data. Very often with very large data sets, they will have some missing fields represented by none values. Say the participant of a survey did not answer this question for some reason. You'll have to filter out those results or replace them with custom values before actually processing the data. So in this case, we're creating a Panda data frame with a few none values dotted around. What a handy function is data frame.isNull, which will return an equivalent data frame of Boolean values that specifies whether this value is none or none, basically non-existent. We can fill those missing values with using multiple functions, say fillNA, replace, interpolate, which will allow us to fill up those values in multiple methods depending on the application that you're doing. Say in this case, we're telling it to fill up every none value with a 2. And that's what we end up with by using fillNA, NA. Another option is to actually just drop the missing values. By using df.drop_na, it will just drop the rows where we have some missing data points. When working with large data sets, it's often simpler to actually drop out this data than to actually try to fill it up. This will definitely result in clearer models. Okay. Any questions before we continue?
No questions.
No questions. Okay. Okay, and it's actually possible to iterate using for loops over rows and columns on Pandas data frame. In this case, we're creating a data frame from this given dictionary, and we can just reference it and iterate over its rows as follows. Here we're getting ij equals from df item row, iter rows. This basically return us I to be the row name, and j to be the actual element inside that row. Basically, here we have the index of our row and the data stored inside of it column-wise. We're also able to actually iterate over columns inside the. Yep, we're also able to iterate over columns in Pandas on Panda data frames by using the apt columns, which will result in the list of columns in this data frame. Okay. Here we're actually printing the third element of every column. So for name it be Kai, age 22, address New York City, and qualification BA. This is basically equivalent to getting the third row. But you might want to do other functionality on those columns, so this functionality is available. Yep. We have many methods that can be applied to data frames. Some of them, an index with given a row label will get us the index of this data. Insert, which allows you to add a column to a data frame. Add allows you to add a data frame to another element twice. Basically addition, subtraction, multiplication, division, checking whether elements are unique, is null, etc. Where Pandas actually shines and is most used is when loading data from files. Panda allows us to load data from a wide variety of file formats like CSV files, JSON files, SQL databases, Excel files, etc., and a lot more. So here we're actually downloading a CSV file from the cloud, and we're loading up its content. As you can see, we're making use of this head method to make sure that our file has loaded up correctly. We can do this very similar functionality on JSON files, where we download the JSON file and we load up its data. This will also result in a table. Usually, Python provides us with a method for loading up JSON file. Python provides us with a built-in library for working with JSON. But Pandas can actually take those JSON files and turn them into data frames, which are much easier to work with when doing machine learning. So let's run this. We just need to download our file. Still lagging a bit. I think let's actually skip that to not waste any more time. We're also able to load from Excel files as follows. We just specify the path to our Excel file, and we can here in this case we need to specify what column in the file to use as an index for our data. This can be either numbers, numeric, or labels to index our data. This here will be translated as the ID column. Another thing you can do with data frames is to actually join them and merge them together. Say you downloaded statistics from multiple websites testing the same thing in multiple countries, and you're looking to merge this data together to perform analysis on the entire data set. Pandas allows you to do so. It has many methods to do this functionality. Say the concat method, which will allow us to create one data frame out of an array of other data frames, a Python list. Here we're passing it two data frames, the F1 and the F2, and we're building up a data frame where both are concatenated. In this case, though, you'll have to have the continuous indices for it to work. Any overlapping indices might cause issues. In case you have, okay. Similarly, you can use the append method to actually concatenate data frames along the axis 0. For some reason, the output here isn't loading. So by the way, anywhere where we're having issues here and it's not loading up the outputs, you can actually check that on your notebooks that are available in the description. In some cases, we might not actually have continuous indices between data frames. In this case, we can actually still use the concatenation method, but we'll specify the ignore indices parameter, which will ignore whatever indices are defined in the original data frames and redefine new numeric indices for the given data. This is particularly used when concatenating large data sets, where the actual index of the data doesn't really matter. It's also possible to concatenate data frames under groups. Say you want to have this data frame constitute a big continuous data frame, but still have a distinction that this data came from, say, this country A, or the other data came from country B. You're able to do so by specifying key parameters. Basically, a key is a group label for every data frame you're concatenating. The length of the keys list should match the length of the frames list. Okay. Pandas also provide a single function called merge, which is an entry point for all these merging operations and runs directly on memory, which runs much faster on very large data frames without the need to create new objects. You can also have data frames that share that reference the same data, but each contain different things. Say here we have the same keys, same IDs for both data frames, but the first one gives us data about the name and the age of a given participant, while the second one gives us his address and qualification. We're able to actually merge the columns of those data frames to build up one large data frame with all this data. As we can see here, still haven't loaded up. That's it. So as you can see, we have the names in each column with Alice and qualifications, and it results in one big data frame with all this data. In some cases, it's also useful to actually keep reference to the ID of given data frames, to the keys of given data frame. Basically, you have a data frame with multiple keys defining it, multiple labels. You're also able to merge along a specific set of labels the data and the data frames using the merge function. And by specifying what keys we're using. Here we're actually merging the key 1 of the first array with key 2 of the second array. With key of first array with key 1 of the second array. Pandas also provide us with a join method. This allows us to join the columns of multiple data frames where the index doesn't really matter. Say, those two data frames could be differently indexed, but it will actually it will actually result in an output that only contains the indices with given data, which isn't loading here again. We're still having problems with this. You can actually check out the outputs in your own. Okay, they're loading up. Yep, in this case, as you can see, even though we have different indices, here we're labeled from K0, K1, K2, K3. Here we have K0, K2, K3, K4. It's still able to merge the arrays, and where data is missing, it will just replace it with nonce. Okay, so that's it for pandas. I'll pass the mic on to Ellie to talk about Scipy and Matplotlib.
Hi everyone, my name is Eli Ayoub and I'm going to be presenting to you the two coming libraries, which are Scipy and Matplotlib. Just let me share my screen. Okay, before I start, I'd like to say that at the end of this section, there's going to be a small coding challenge, and if any of you solved it, they're going to receive in about a week from now a certificate that they solved the coding challenge. And therefore, I urge you all to pay close attention and to open the notebooks that are in the description to follow up with me as I explain to you. So I'm going to start first with Scipy, which is library that's built mainly on top of NumPy for engineering and mathematical applications. So it's kind of similar to NumPy, but it will have more special functions and just more things to do with it. So to start, I'm gonna obviously import Scipy, and I'm gonna import NumPy as well because I'm gonna be using it throughout. Let's start with some of these special functions that Scipy includes. So first thing, we're gonna create an array called demo where we're gonna arrange the first 10 integers. That would be from 0 to 9. And I'm gonna import the special package so I can use the special functions that I just mentioned. One of those functions would be the cubic root function. And to call it, I can just do special that I just imported .cbrt of demo, and that will return an array with the cubic roots of all the elements in demo, as you can see. Other special functions would be the x2, which will return the 2 exponent x, where x is the value in demo because I gave it demo as an argument. Same thing for x10, it will return 10 exponent x. Some of the other ones would be the permutation and the combination that would be mostly used in probability and statistics or any other course or application involving probabilities and distributions. So you would say, I want to calculate the permutation of 5 over 2, or I want to calculate the combination of 5 over 2. Now for repetition here, the usual combination that you see in your statistics course is with no repetition. So that's why we gave it repetition equals false here. You can give it repetition equals to true, and it will account for repetition while calculating the combination. Moving on to more important parts of the Scipy library, it's for the linear algebra and later for the interpolation. As you may know, NumPy also has a linear algebra package of its own. However, Scipy's just has more function and it's kind of faster to use. So let's start by importing it. And I'm going to start by solving this linear equation of 2 unknowns, x plus y equals 2, x plus 3y equals 9. So if you're familiar with matrices, I can write this one as ax equals b, where a contains the coefficients of the variables of the equations, while b contains the right-hand side elements, which are 2 and 9. As you can see, we created them right here in lines 6 and 7. So these would be the coefficients of the variables, and these would be the elements of the right-hand side. Now, if I want to solve this system, I can simply call linalg.solve, and I give it the coefficients of the variables, and I will give it also the right-hand side, and it will solve it for me. It will return x and y, as you can see. Another application is to find the determinant of a matrix. I can just create any matrix, and I'm going to do linalg.det, which stands for determinant of A, and it will return the determinant, which in this case is -2. Now, which brings me to the final section of Scipy. Scipy is a really small library for now because you're not going to really use it while working on machine learning. However, if you're ever going to use it, it's going to be mainly for this section here, which is interpolation. So let's get to that. As you know, interpolation is determining values between specific sets of values that we do not have. So let's look at this graph over here. So I have these scattered points over here. Now let's not worry about how we plotted those points because we're gonna get to that in the next section, which is Matplotlib. But let us focus on the interpolation part. So I have these points here, and I would like to calculate the position of points between them, and that would be interpolation. So how can I do that? So in this code chunk, we just used that to plot the figure. We discretized our x and y space. We got our x and we got our y's. So the function that's plotted here would be cosine x squared over 3 plus 4. Okay, so now I want to interpolate positions between those points that you see here. How can I do that? Well, Scipy has interpolation functions that are predefined. And to create one of them, I can just simply do f1, which I will call my function, equals interpolate dot interp1d xy. So I will give it the data that I want to interpolate between. So I want this function f1 to interpolate between the data of the points of position x and y, which are these ones. X and y we defined here before. So I will give it x and y, and I will give it the interpolation kind. There are many interpolation kind, like linear, quadratic, cubic. It's just how would you want to connect those dots? How would you like to interpolate between them? So here we define two functions, one that will interpolate linearly between the points, and the second one will interpolate using a cubic polynomial between them. Please keep in mind that f1 and f2 are functions that I define and that I will use later. Those functions will take inputs, x values, and they will use them to return y values. Now let's see how that works. As you can see here, I created a new set of x values scattered between 0 and 4 with 30 values, actually. This is the number of values. So as you can see before, the x values were between 0 and 4 too, but I had 12 points. Now I have 30 points, and that will lead me to other x values. Now, how can I calculate the position of these x values on this plot? That's where I'm going to use the functions f1 and f2 that I just defined. So we don't really care about now about how we plotted it, as this will be mentioned in the coming section about Matplotlib. But let us look at the following parts here. So you see, I plotted f1 of x new. f1 is the interpolate function that I just defined previously, and I gave it the x values, the new x values that I just defined. And I told it to plot it in continuous line. And then I did f2, which will interpolate using a cubical polynomial. And I gave it the same values of x's, but I told it to plot it in dashed lines, just for the sake of comparison, so we would see the different ones in the plot. Well, let's look at the plot. As you can see, the blue points are the main data points that I first created, which are the accurate point, while the orange and the green lines are the interpolated data. And as you can see, the orange one is the linear one. It's f1 that we defined here to be linear. As you can see, the points are connected with lines. As for the cubic one, the points are connected with a spline, and it's technically a third order polynomial because I specified the interpolation type to be cubic. For Scipy, this would be it. There are many more stuff like to go over in Scipy, but for machine learning purposes, this would be everything that you would use if you would ever use. Any questions?
No questions.
Okay, moving on to Matplotlib. Now this is the chunk of this section. Let me share it with you 1 second. Okay, I hope you can see my screen. So what is Matplotlib? Well, it's also built on top of Numpy. As you will see, we're going to use Numpy a lot in Matplotlib, and it just used to visualize stuff. You can plot line charts, bar charts, pie charts, surfaces, or even plot images, as you will see in this section. So first of all, to use Matplotlib, you obviously have to import it by doing import matplotlib.pyplot, as I'm going to call it PLT for ease of use. And I'm going to import Numpy as well because I'm going to be using it extensively. So let's start first with plotting functions or line plots, the regular plots that you usually see. Let's take this function, for example, radical x minus cosine squared of 3x. I would like to plot this function. So what I will do, I will start by discretizing the x space. I'm going to take values between 0 and 20, and I want 1,000 values between 0 and 20. Now I will calculate the y values for these x values. I will store them in an array called y1. Now let's plot it simply. I can simply plot it to visualize it fast by simply doing plt.plot, the x value and the y value, and I'll type plot.show so I can see my plot. And it will simply just generate a plot for me where I can easily and quickly visualize my data. But what if I want to customize my plots? I want to add stuff, fix some stuff in them. How can I do that? Let's look at this customized line plot. As you can see, I plotted the same function as earlier, but with many extra stuff. How did I do that? Well, first of all, I plotted my figure by doing the same thing and by adding this argument over here. As you can see, this is k and double dash. Now, this is a color and line type argument. So k indicates color black in Python. and Matplotlib specifically. Let's say I used B instead of K, my plot would have been blue instead of black. If I used J or G, it would have been green instead of black. And the double dashes here will give me a dashed plot. For example, I could have put an O here and it would be plotted with like small points instead. If you want to know more about these stuff, you can head to the documentation. I've put a link in the top of this section, and you can see all the codes here, what to write to have what color and what type of line. Okay, I also want to add a label to my x-axis here. As you can see, I have x under this label. So to do that, I wrote plot.xLabel x, and I did the same thing for the y label. Now, let's say I want to limit my plot. I want it to be between certain values for the x-axis and certain values for the y-axis. To do that, I have to use plt.xlim, which stands for the x limit, obviously, and I set it to 0 and 20. And the same thing for the y limit, which I set between -1 and 5. I also gave my plot a title, which is the mathematical equation of this function that I'm plotting. And I activated the grid. As you can see, this photo, this plot here is gridded, while this one is not. To do that, all you have to do is call plt.grid. And finally, to show your plot, don't forget to type plt.show. Now, one thing I can also do is plot multiple functions on the same plot. Let's look at this one here. It has 2 functions on the same plot. So to do that, I defined another function, which is y2, that will use the same x values, but it will give me different sets of y values. So it's another function. And to plot both functions, I will start by plotting the first one and giving its setting parameters. So this is x and y1. These are the first one that I plotted. And by B, it means blue. And 1 dash means a straight, like filled line. And after that, I can add the information for my second function, which is also x. That's the x values for my second functions, and y2 would be the y values for my second functions. And I want my second function to be black and to have a dashed line pattern. So that's what I added over here. Now I labeled my plot and I set my limits and the title as before, but the extra thing here is I set a legend. Because I have 2 functions, I need to know which one is which. So this plot must have a legend. And to do that, you will have to do plt.legend, and you will give an array of strings containing the legends. You will see I added here a parameter, loc equals lower right. Now this one will set the location of my legend. As you can see here, my legend is in the lower right corner of this plot. And that's all I'm doing. Please keep in mind that this backslash here just means that I will be continuing my string on the second line. So it's nothing really. Okay, this would be plotting functions. Are there any questions on this section?
Someone asked, what happens if you don't define the number of points?
If you don't define the number of points, is that when you're doing linspace, when I'm setting the number of points here?
I would assume so.
If that's what you mean, then nothing will happen. Then it's not going to know how much points you want to use between them. And please keep in mind that for a function to be generated correctly and for you to visualize a correct pattern of a function, it must be well discretized. So I cannot come here and, for example, give it 5 points and just hope to see the function. It's not going to look like anything if I give it 5 points. And the more my function is oscillating, the more I would have to discretize it. So you always have to specify a number of points, and that number of points must be like specific to the function that I'm trying to plot. For example, for this function here, I cannot come and give it 10 points. I have to give it a lot of points for it to be plotted correctly. Now for a simpler function, maybe for a line, if I wanted a line, I can simply give it 2 points and it would plot it 100% accurate. So I hope that answers your question. Anything else?
No, that's it.
Okay, moving on to scatter plots. So I will start by creating the data that I'm going to plot as usual. I'm going to start by creating my x and y values for the points that I'm going to be plotting. So to do that, I'm taking 100 random values and I'm going to multiply them by 3. So my values would be between 0 and 3 because this one will give me values between 0 and 1. And if I multiply that by 3, my values will be between 0 and 3. Okay, so now I have my arrays of x and y values. And simply to plot them on a scatter plot, I would use plt.scatter, and I give it the x positions and the y positions. And as usual, plt.show to see my plot. So this is a simple scatter plot. But once again, how can I customize my scatter plot? Well, let's look at this example here. In this example, we're going to be plotting here, this scatter plot that you can see here. How can I do that? Well, first of all, I'm going to start by creating an array with the dimensions 300 times 2. That means this array has 300 rows and 2 columns. And as you can see, this one is not random.rand, it's randn. And what this will do is it will generate numbers based on the normal distribution. If you know it from statistics, it's the bell curve. Now what this will do, it will generate numbers centered around 0 that look like the bell curve. So what I'm going to do here is I'm going to take the first 100 rows. As you can see, I'm calling the first 100 rows, and I'm adding to them 3. What that would do is, remember that this points array is based on the bell curve, and it's centered around 0. Now I added 3 to it, so now this part of it is centered around 3 instead of being centered around 0. Same thing for the second 100 points. I centered it around 6 instead of having it around 0. Now I'm going to create a color array because I don't want all my scatter points to be in the same color. I want the ones centered around 0 to be a different color than those centered around 3, than those centered around 6. So what I'm going to do is I'm going to create a color array. Now I started by defining it to be all zeros. And I changed the color of the first 100 points and the color of the second 100 points. Now these values 1 and 2 that I'm giving here are color orders. So it would know how to order the colors on the plot. Same thing for the size. Now I can give it size values for points. And I want the points centered around 0 to be of a different size than those centered around 3, than those centered around 6. So I started by creating a size array, and I set it as np_numpy.ones 300. So it will give me an array of ones, that's all ones, and I'm multiplying it by 30. So now all the array is 30. Now I changed the size of the first 100 points to 20, and I changed the size of the second 100 points to 10. And that leaves me with 100 points of size 10, 100 points of size 20, and 100 points of size 30, those that I did not change here. Okay, so now I'm ready to plot them. So I'm plotting a scatter plot. I'm giving it, for the x values, remember that here I generated an array of 300 rows and 2 columns, where the first column contains the x values I want to use, and the second column contains the y values I want to use. So to plot the x values, I'm going to take the array points. I'm going to take all rows. This symbol here, as you should know by now from the NumPy section, means that I want to call all rows. And the 0 here means that I want to call the column with index 0, so the first column. Now, same thing here, all rows, but the column with index 1, so the second column, which are my y values. So I'm kind of giving it here x values and here y values. Now C equals, this parameter will indicate color. And so I will give it the color array that I generated here, and same for the size. So for the first 100, it will give them color based on this that I defined here. For the second 100, same thing for the size. And here I'm just doing the usual plotting, setting my limits and my labels and my title. And this would be the resulting plot. Any questions about scatter plots? I didn't hear you. Is that a yes or no?
No, there's nothing.
Okay, let's move to histograms. As usual, I'm going to start by generating some data sets. Once again, I'm generating using the randn function, which will give me points that are based on the normal distribution, the bell curve. And here I'm generating 50,000 points. And remember, those will be centered around 0 by default. So let's plot. I can plot it in histogram right away by using plt.hist and give it the data. And as you can see, this resembles the bell-shaped curve. So here on the x-axis, I have the values. On the y-axis, I have the number of samples in this range. So, but let's look at this histogram. It's not really defined. We can see like a trend following the bell curve, but we can't really see the bell curve. So let's customize this histogram to make it look more like the bell curve, to make it look something like this. How can I do that? So I'm generating data again, 50,000 points using rand_n, which will be based on the bell curve, centered around 0, and I added 2 to the whole set. So what will happen is now it will be centered around 2 instead of being centered around 0. And we can see that clearly here. It's centered around 2. Okay, now simply I can go to plot the histogram. I want to plot my data. Now the number of bins will be the number of like how many rectangles do I want to use in my histogram. And as you see, this one, by default, it has 10. Now I'm setting it to 80. So I'm using 8 times more rectangles than in this one. And you can see that clear. Look how more defined this histogram is. Color, I'm giving the red color because I want it to be red. And the range is from where to where I want my histogram to be. Now, please notice here that the number of bins will be the range divided by the number of bins. So like even let's look at here between -2 and like -1.8. Let's say there's nothing here. There's no values, but the bins here are being taken into account for that small value. So like the red bins that you see here, they're not 80 because I used 80 bins for the range -2, 6. Now, even if here on -2 I have no bins, but it accounted for them. So like the red bins here are not 80, are a little bit less than that. So that's something to keep into account once you're setting a range for a histogram. I hope that makes sense to you. And that would be it for histograms. That's all what you would need from histograms. Any questions?
No questions.
Okay, up next is bar charts. As usual, start by generating our data. So I'm setting x values, and these would be the location of my bars on the plot. And I want the height of those bars. How high do I want my bar to be? So I'm going to define those two simply, and I'm going to plot them right away to just have a fast and simple bar plot. You can see it here. You can look at the x points. They're the same as the one I defined up there, and the same thing for the height. Now let's customize those bar charts. Now I chose this section on bar charts to implement something new here, and this is the subplots that I'm gonna explain in a sec. So once again, I'm using x positions and height. Now this here, plt.figure fig size equals 14.6. What is this? Now this is, I'm setting the size of my figure. Look at this figure. It's kind of bigger than the ones I've been showing you previously. And that's because I changed the figure size. Now the 14 and the 6 are in inches. So I want it to be 14 inches wide and 6 inches high. Okay, let's look at subplots. So let's say I want to do multiple plots in one figure, just like in this section. What I can do is I can define subplots. You will notice that I did plt.subplot and I gave it like a number here. What's this number? So you can think of the first two numbers as an array of size 1, 3. So I want to have one row and I want to have 3 columns. Let's look here. I have one row and I have 3 columns in it, 3 plots. Now the third value would be which one of those am I working on now? So 131 would mean I'm working on the first plot that's in the form of one row and 3 columns. So I'm working on this one. Now, if you look here, I used 132 because I want to operate on the second plot, and I used 133 because I want to operate on the third plot. Okay, to plot the first bar, I plotted x, the height, and I gave a specific width for my bar, because if you look at it by default here, the bar will be 0.8 wide. I want it to be 0.5, and I want to change its color and its edge color. The edge color, as you can see around my bars, I have some like black lines. And the line width of that edge. So as you can see, they're very customizable. You can change a lot of properties. Those are just ones I put for you to see. Labels and limits and titles, nothing new. For the second subplot, once again, I did the same thing. I changed the color to green for this one. But for this one, I don't want the x values to be numbers. I want them to be letters. So what I did is I added tick labels, A, B, and C. But please note here that I'm still using x. Why am I still using x? It's because I'm telling it where I want to plot it. I'm telling it I want to plot them at 1, 2, and 4. Let's look at the plot. As you can see, A is at 1, B is at 2, but C is not at 3, C is at 4. But instead of seeing numbers, I'm seeing the letters that I specified here. So for the third plot, I'm going to do the same thing, plot the bar chart. But notice that this time, instead of giving x values, I gave an array of strings containing C1, C2, and C3. Now, in this case, my bar chart will be categorical rather than based on x locations. So if I gave it 3 strings, it will automatically be divided into 3. And it will have the data that I give second, which is the height data. So as you can see, this one, all 3 are equally distant. This would be it for bar charts. Any questions?
No questions.
Okay, moving on to pie charts. Okay. Once again, generating the data. I want my labels for my pie chart to be from year 1 to 4. And here I'm going to give the size of every section. Now these sizes are in percentage. So if you sum these, they will sum up to 100. I give it how much percent of my pie chart do I want it to be. And if I want to plot it right away, I can simply do plot pies. I give it the sizes and the labels. Labels equals labels. This is the one I created right here. And obviously plt.show, and this would be my simple pie chart. Now let's customize this pie chart. One thing I can do is, let's say I want to make a piece appear out of the other pieces. Like here, look at the orange and the red piece. You can see they're kind of away from the chart. How do I do that? I can do that by setting an explode array. So explode equals, so for the first one, I don't want it to be exploded. I want the second and the fourth one to be exploded. So I'm going to give it a value of how much I want it to be away from my pie chart. And then I'm going to plot my pie chart using the same method, plt.py. I'm going to plot the sizes and the following labels. But this time, I'm going to add an explode value from this array for each one. And I want to make my pie chart bigger. Typically, its radius will be 1, but I want to make mine 1.1. Here, auto PCT, that will be the format of the value that I want to show on my plot. So like as you can see here inside, I have 1.1f%. So 1.1f means I want to have floats with the one decimal point, and I want it to be a percentage. And that's what you see here on the plot. I have 14%, 23.0%. Shadow equals true. You can see the shadow on the edges of the pie plot. And start angle equals 90. So instead of starting my plot from 0, as you can see here, my plot starts from angle 0. I want it to start from 90. So look at the blue section now. It's starting from an angle of 90 degrees. This would be it also for pie charts. Any questions?
We have one from bar charts. I guess it came in after the delay. Can you use functions inside bar charts?
Sorry, can you repeat that?
Can you use functions in bar charts?
What do you mean by using functions in bar charts?
You're going to have to wait 10 seconds.
Yeah, that's fine. If you mean by values that are deducted from functions, then yeah, I should just, when I got my data here in height, instead of just entering the data myself, I can have it store like the return values of a function. If that's what you're asking, then yeah, sure. Like you would just have here, instead of input data, you would have a function and with its returned values or arrays or whatever you're trying to plot on a bar chart. I hope this answers your question. If not, please let us know.
I'll let you know if they add anything.
Okay, moving on in the meantime.
Yeah, they mean instead of giving them manual values.
Yeah, so I answered that question, I hope. Yeah, surface plots. Okay, now what if I want to plot a 3D surface using Matplotlib? Well, definitely I can do that. Let's say I have this surface, z equal x squared y plus y squared x minus 4xy plus 1. I want to plot this surface. How do I do that? Well, as you see here, I have 3 variables, x, y, and z. So I need to start by discretizing 2 of them, which are x and y. I want them to be between -2 and 2, and I'm using 1,000 points for each. Now, to plot a surface, it has to be based on a mesh. The x and y points must be interconnected. And to do that, I'm going to take x and y, and I'm going to mesh them using the Numpy function mesh grid. So I'm going to have them meshed using this function here. After doing that, I'm ready to plot my surface. Now let's define my z values after doing that. So I'm going to use the x and the y values that I just meshed to get my z values. So now I have my x values, my y values, and my z values, and I'm ready to plot my surface. How would I do that? Well, once again, I'm changing the size of the figure only here, so it would appear better. Okay. To plot 3D surfaces, I need to use the 3D axes, because if you noticed before, regular plots in Matplotlib come in with 2 axes, the x and the y axes. But for this one, I need 3 because I have 3 dimensions. So to do that, I have to get 3D axes. I will type ax, that I just named that short for axes, equals plt.gca, and I want to specify that my projection type is 3D. And GCA stands for get current axes, by the way. And I'm setting that I want them to be 3D. Now I will use these axes to plot on them what I want to plot. To plot a surface, I will have to use the function plot surface. So I'm ax.plot surface. I'm giving it my x values, my y values, and my z values. And I'm specifying the width of the lines that are going to be delineating every point. The edge color, K, remember that K means black. And C map is color map. So I'm just giving it one of the built-in color maps, which is called hot. As you can see, this surface here, it looks kind of like a heat map from yellow to red. So there are many color maps that you can use. And the alpha means the transparency of my surface. As you can see, this surface is kind of transparent a little bit. That's set by this alpha here. Now, if I want to set labels for a 3D plot, remember that before we used to use plt.x label, plt.y label. Here, I'm going to use instead the functions that are set for 3D axes that I just created here to plot a surface. And these would be ax.set x label, ax.set y label, and set z label. Same thing for the limits. Instead of having plt.lim.xlim, I will have ax.set xlim, set ylim, set zlim. Same thing for the title. And this would be it. Any questions before we move to the final section?
No, nothing yet.
Okay, so I can even plot images in Matplotlib. And to do that, I need a library called Pillow. So I'm going to import this library, and I need a certain object from it, which is image. So to do that, I'm going to do from PIL, which is short for pillow, import image. Okay, so for a photo, I use this function, this command here, which is wget, that allows me to download anything from the internet into my Google Colab space. And I chose a photo of a nice puppy that I found on Google because we all like puppies, I hope. And I'm going to open this image using image.open, and I'm going to give it the name of the image that I just downloaded. As you can see here, it's downloading, and I have my image now. Now, one thing to note is that what is an image? An image is a 3-dimensional array where the first two dimensions would be the size of this image, like how wide is it and how high is it, how many pixels it has, what's its resolution. And the third dimension would be for colors, for RGB colors. As you know, colors on an image are defined by 3 values between the red, green, and blue spectrum. I can use this image that I loaded, and I want to see it as a NumPy array, because as I said, an image is an array. So let's see it. I converted it to a NumPy array, and let's look at its shape. So the shape is 430, 760, and 3. So as you can see, it's 3-dimensional. This is its size. It is 43 pixels high and 760 pixels wide. And it has 3 values for colors, one for red, one for blue, and one for green. And this would be my image. This would be my image as an array. As you can see, it's 3-dimensional. And these are the color values for my RGB values. And please note that these values are between 0 and 255. It's 8-bit. Okay, let's say I want to plot my image. So remember that this array here that I called array is nothing but my image, because I set it here to be my image. So if I want to plot it, I can simply use plt.imshow and give it array and plt.show as usual. And here's my image plotted in Matplotlib. Okay, now an important part of machine learning is customizing images if I want to use them for, let's say, computer vision applications. So we're going to see something similar to that here, how I'm going to use this image and I'm going to do some stuff on it. I'm going to customize it. So let's say, for example, I want to get the heat map of its image to turn it into another scale, like we will do later. We're going to use grayscale. So to get the heat map, what I will do is, instead of having 3 colors for the RGB values, I'm going to collapse that dimension and just have one value, which is the average of these RGB values. Remember, first it has 3 values, one for red, one for green, one for blue in the 3rd dimension. I'm going to collapse that dimension and just have one value there. So to do that, I'm calculating the mean on the 2nd axis. Now remember, indexes start from 0, so 2 would be the 3rd dimension. So I'm getting the mean of the values on the 3rd dimension instead of having a 3rd dimension. Now let's look at the heat map. As you can see here, now I have my heat map after collapsing my 3rd dimension by getting its mean. And now I can use this heat map to generate my, give it a color map, which is gray, short for grayscale. And let's look at it. Now I have the same image that I had earlier, but in grayscale. And this would be it for this whole Matplotlib section. And up next, we're going to have the exercise that I mentioned in the beginning. But before that, do we have any questions here?
Someone's asking, do you have to turn your image into an array before showing?
Actually, instead of here plotting, where is it here? When I used imshow, instead of giving the array, I could have given im itself, which is my image, and it would have given the exact same results. I just turned it into an array to explain to you that an image is nothing but an array. That's all. But please bear in mind, for example, to generate the heat map, I need to do that on an array. So I collapsed the 3rd dimension of an array. Anything else?
That was it.
Okay, I guess we can go to the exercise now that I urge all of you to try to do, because it's not an easy exercise. It's not a hard one either. It's actually simple. It's just gonna require some critical thinking from your part. So I urge all of you to try to do it. Let me just explain it to you at first. So as you can see, we have a scatter plot, obviously, here, and we have 3 concentric donuts here. And this is what you're gonna plot following this data. So the first donut will have 500 points, while the second one has 1,000 points, and the third donut has 1,500 points. Now the random points of the first donut are between the value, like the radius value 3 and 7, for the second one between 8 and 12, and for the third one between 13 and 17. Those are the ranges of the radiuses of these donuts. And you have to adhere to the format and color code provided in the sample image. So I urge you all to try to solve this problem, and we're going to give you some time now, like maybe between 10 minutes or something like that, to solve it. And if any one of you manages to solve it, they're going to receive a certificate in like a week that they solved this workshop's coding challenge. Also, everyone who attends the three ML sessions will receive a certificate at the end, but there will be a specific one for this challenge. So please go ahead and just so we wouldn't waste some time, I'd like to know, please, if you're gonna try and attempt to solve it, please type that in the YouTube comment section, so we would know that some of you are actually attempting to solve it, and we wouldn't be waiting for no one. Please do that. Solving.
Yeah, sure. I'll let you. Yeah, someone says they're going to try, but it might take them some time.
Okay, yeah, no problem. We plan on giving you 10 minutes here, so you have like 10 minutes, maybe a little bit more, a little bit less, depends on the time to try and solve it yourself. So please go ahead. And you have to, if you do solve it, or whatever you solve, you don't have to solve it correctly, please upload a screenshot of your plot on the submission link that's in the description. So I will be looking at them. It doesn't have to be right. Just show me your progress, or where you got, or what were you able to do correctly, what was hard. So like no need to upload it only if it's correct. You can upload whatever you get to.
Yeah, for
And
sure.
at the end,
Yeah, sorry to cut you off. No, I just wanted to say that if you have no visible output because you keep getting errors, or you're struggling with it within the 10-minute frame, just upload like a screenshot of the code part. So no need to just, if there's no output, no output. Just take the code and screenshot it. Sorry for cutting you off.
yeah, no worries. Just show us your progress. Doesn't need to be correct. Of course, bonus points if you do it correctly. Props to you. But like, just show us your progress. And at the end of these 10 minutes, I'm gonna be walking you through the solution myself. In the meantime, if anyone has any question related to any of the material that I covered in Sci-Fi or Matplotlib, please do not hesitate to type your question in the chat so I can answer them while we wait for people to solve. No questions whatsoever?
No.
All right. By the way, for those of you attempting to solve it, do not forget to import numpy and matplotlib.pyplot before starting.
Okay, guys. So in the meantime, I'm just going to, just make like a brief announcement, just because some people aren't actually solving the exercise, so we don't want to keep them waiting, in this, endless silence. So we're gonna continue and go over the solution for everything in probably a few minutes. But before we do that, I just want to share my screen very briefly. So let me do this. So I'm gonna stop your sharing and okay. So you're supposed to see my slides. So yeah, I just want to talk about our upcoming event. So like we said at the start of this event, this is part of a three-part machine learning series. The way the series is structured is the following. So we have these three parts. The first part was Intro to Python. We're done. Check mark, everything's good. If you're not done, you can always go back to it and watch the recording. Number two is these libraries. So what you just attended today, also check mark. And number three is basic machine learning with Python and TensorFlow. And you'll be seeing that next Friday, same time as today, so in exactly a week. So if you feel like today's material, you just need some time to digest, you can feel free to look over the notebooks, play around with them, experiment with some things, changing the code and all that. And then attending with us next Friday so you can start your machine learning journey for real. Okay, so that's for the next event regarding this series. However, we do have other events also in the works. So you know that we never stop working as a club and we're always attempting to give you guys the most. So we have another event before our final machine learning event actually. So this will be on Monday. So when I say on Monday, yeah, in 3 days, this event will actually be not related to machine learning. You'll receive announcement emails and promotions and all that on our social media. We're going to talk about open source because this is Hacktoberfest. So October is Hacktoberfest. It's a month to celebrate open source and talk about open source software. So I will be presenting this event myself, and I really look forward to seeing you guys there so we can talk about open source, contributing, pull requests, GitHub, like what goes on with all of those things, what's really happening. This should be able to give you an insight. It will be like a short talk and not really an in-depth workshop. So yeah, I look forward to seeing you guys there. Like I said, you'll receive promos and all that. It will be on Monday at 7 p.m. And finally, the last thing I want to show you guys is another special event that we have. This one is happening after ML3. It's happening Wednesday, October 21st at 6 p.m. We have a researcher from the Cairo University Quantum Computing Center. This is a center that works with IBM. And Sarah is actually a PhD researcher in quantum computing, and she's going to be our guest to actually talk about quantum computing, some concepts, and how we work with it with Python. Obviously, she cannot cover the entire thing, so it will be a brief introduction. So we also look forward to seeing you guys there. And I'm just gonna wrap up with this, and then let you guys go back to your solving and all that. Okay, so yeah, see you guys hopefully on Monday and on Friday and the week after.
Okay, guys, we're gonna wrap up the submission for this exercise in a minute. So please start submitting what you're writing, whether you finished it or not. Like, that's okay. I just want to see your progress and what you did. Please go ahead and submit it. You don't have any submissions yet. When you do submit it, please say on the YouTube comments that you're submitting. So just I would make sure that you submit it, because right now it says that I have 0 responses.
Also, guys, one thing we want to mention before wrapping up as well is that we see a lot of um, a lot of people, rewatching our videos on the YouTube channel and from our, YouTube analytics, and we see like people going back over the older material and all that, and we really support that. But we also want to tell you something that please, if you do that, and if you have any questions, please ask on the Slack. So the core team is there to assist you. If you feel like there is something that was ambiguous in one of the presentations, feel free to ask a question about it on Slack. Well, they might not reply immediately, because with everything and these all different types of events, but this will always be somewhere for you to ask any sort of dev questions ever. Okay, just keep that in mind. And to join our Slack, you can refer to our social media for the link. So you'll find it in our Instagram and Twitter bios.
Guys, is anyone going to submit anything, or should I just close the submission and just go over the solution? Please comment on the YouTube live. Okay, no answers. So I expect that none of you is going to submit. That's all right. So I'm going to walk you over the solution now for those of you who are interested in how to solve such a problem. Well, as you can see here, we have random points that are just scattered over some donut shapes. Now, if you want to think of this, I want to generate x and y values. You probably guessed that. But how can I generate x and y values in patterns like this? As you can see, they follow this donut pattern. Now, the trick to solving this problem is figuring out that instead of having x and y position directly, what I will need to have is a random radius and a random angle instead. Okay, so I'm gonna solve it right here. So we're going to start by, as we saw, we have 500 points in the small one, 1,000, then 1,500. And if you sum those points, it means we have 3,000 points. Therefore, I'm going to create 3,000 random points. Now, bear in mind, these points will be between 0 and 2. I'm going to add these values. And I want the 500, we said. So I want the first 500 values to be in the range that's specified. And how can I do that? So I know that it already has a value between 0 and 1. How can I get that value from between 0 and 1 to between 3 and 7? Well, simply, I can multiply it by 3 and add 4. Actually, multiply it by 4 and add 3. If I multiply it by 4, I will have a value between 0 and 4. And if I add 3 to that, my value will become between 3 and 7. Now I will do the same thing for the others. Now, the next 1,000 points, this would be between 500 and 1,500. Now I want these to be in the value of, as you can see here, I have them between 8 and 12. And to do that, I'm going to once again multiply by 4. And this time I'm going to add 8. Now for the last set, I'm going to have from 1,500 to 3,000. What I'm going to do here is I'm going to have them multiplied by 4 once again. And this time I'm going to add here 13. Okay, so now I generated my radius values. What do I need to do next? So as we said, we need angles now. How can I generate angles? So to generate the angles, I will get once again random values, 3,000 random value for angles. Okay, but we know, now keep in mind that I'm going to be using angles in radians. So how do I do that? Well, simply I need to multiply by 2 pi. So this is all what I have to do now. And now I have this angle, in a random angle in radians. Okay, now I am ready to generate my x and my y values. So I'm going to do x equals, how do I get my x value if I have a radius and an angle? Well, simply I do the radius multiplied by the cosine of the angle. So what I'm going to do here is for radius, and I'm going to multiply by n numpy dot cosine, and I'm going to give the angle. And like that, I now have my x values for my random points. Now let me get my y values. To do that, I will do the same, but instead of cosine, I'm going to be using sine of my values. So now I have my x and y values of all the points. Remember, we started by generating a random radius. Random radiuses between 8 and 12, and 1,500 random radiuses between 13 and 17. And then I generated 3,000 random angles. So I would have them scattered in a circular shape randomly. And from those, I can compute my x and y using radius times the cosine of the angle and radius times the sine of the angle. I will have x and y positions. Now we also see that I have different colors for each of these donuts. So what I'm going to do is I'm going to set a color pattern for each of those. So to do that at first, I'm going to start by specifying one that's all zeros. And I want it to be, we have 3,000 points. So let's give it 3,000 points. Okay, next I want to change the color of certain ones. So I want the inner one to have the lowest value. So I'm gonna keep that one. I don't want to change that one. I want to keep it have the lowest value. So I'm gonna start by changing the color of the second donut. And let's say I'm gonna set it to 1. I'm gonna do the same for this time. I'm gonna obviously set it to 2. Okay, so now I will have a specific color. Now what else do I need to do? I need to plot them. To do that, what I'm gonna do, as you can see, this is a scatter plot. Scatter. So I have to specify my data. These are my x values. These are my y values. And I also need to specify the color using the color array that I just did before. And to do that, I'm going to put C. C is the parameter for color. And I also called my array C. So I'm going to use C equals to C. And I'm going to change the size of these. I'm going to set them to a size of 10. Let's say it's 10 of the, I'm going to set all points to size 10. And finally, I'm going to show my plot, and hopefully I didn't do any mistakes. Let's give it a try. Oh, didn't import Numpy.
Line 7, you have a plus instead of equals. Line 8 now.
Yeah, that too. Hopefully it works now. Okay, there it is. As you can see, every time I press play again, I will have other random points, because remember that all points are generated by random. You will notice slight changes in the donuts. And this would be how to solve this problem. Was anyone close? Does anyone have any comments, any questions, any concerns, please?
Give it like a minute for the delay to set in, and
yeah.
We have nothing yet.
No questions?
No, nothing.
Okay, in that case, thank you for attending my part, and I'm gonna pass it back to Hala to wrap it up.
yeah, okay. So I'm just gonna, like recap real quick without even sharing my screen. So like I said, ML3 will happen in exactly 1 week, where we will be doing beginner ML with Python. Now, on the other hand, We have two other events unrelated to machine learning for those of you who are interested. You will receive promotions. You will see promotions on our social media. So an event on Hacktoberfest, so on open source software in general, how to contribute, GitHub, Git, pull requests, what are pull requests, all those things. So stay tuned for that if you're into open source or if you've always been interested but you never actually went there. And another thing, we have a quantum computing event on the 21st. So you'll get more details on that later on. And this is with an actual PhD researcher in quantum computing. Otherwise, there's nothing else from my end. Thank you very much for attending. We know it was a long session, but hopefully it will benefit you and you'll have found it useful or something to refer to at least. If you haven't RSVP'd yet, please do so because if you don't, contact you with the follow-up information. So the slides, the notebooks, all that. Bye bye.
One last thing for those of you who tried to solve it, a couple people, you can practice now that you know the solution by trying to add a fourth donut to the set. So try to do it yourself and edit the code to add a fourth donut to the set.
Actually, we'll maybe resend that inside the email and mention it and keep the form open over the weekend. What do you think?
Yeah, sounds great. I'd be very pleased to see what you guys came up with and if you were able to solve it yourself.
Yeah.